Now, where do we go from here? Well, naturally enough, we want to consider more than one subset. So let's look at the possibilities when we have more than one set at hand. Bear in mind that there is an abstract universal set chugging along in the background, providing elements from which you're drawing subsets. Now, suppose we have a second subset of omega. So now let's say we have a set A, and naturally enough we call the next set B. Well, what could the relationships between A and B be? Well, both A and B represent subsets of this omega, and I've shown you visually a schema where it is clear that every element in A in the particular setting I'm envisaging is contained in the collection B that I'm showing you. I have not told you exactly what omega is and what A is and what B are, but whatever that underlying abstract relationship, I'm saying that this kind of picture connotes a membership, an inclusion. Every member of A in this setting is in B, or A itself is a subset of B. Now, two generic sets don't necessarily have to have this kind of inclusion relationship. So, at the other end of the spectrum, we could have a setting where A and B are subsets of some omega, and they share no elements whatsoever. This turns out to be a very important basic concept. It's visually clear. You have two collections, and they do not overlap. If that is the case, we see that these subsets are disjoint, and we create some more compact mathematical notation to capture the idea that two sets are disjoint. We write A, and then a symbol denoting a cup, upside down, B. This, in words, we say A intersection B, and this is a small and quick preview of the set operations intersections, which we'll encounter on the next slide. And we say that A cup B, A intersection B, is empty. We say the intersection of A and B is empty. In alternative language, we say that A and B are disjoint. And what we mean by all of this is that A and B share no elements in common. There is no omega which is in A and in B. Of course, these are not the only two possibilities. More typically, we'll get something like the picture in the middle of your screen, where you have two subsets of an abstract set omega, and they overlap. They are not mutually exclusive, they are not disjoint, nor is one completely contained in another. Each of them has elements, little omega, which the other does not have. And again, this is visually clear in this kind of setting, even though I have not specified for you what the sets are. But they also contain some elements from the original universal set, which are common to both. Okay, and this kind of picture is more generic, and it behooves us to look at it and say, well, okay, if we have a setting like this, where we have two abstract subsets of some abstract universal set, and they have some kind of relationship like this, what can I do with them? Well, naturally enough, we can construct more subsets, richer subsets from these basic subsets. And this is where the heart of the nomenclature, the terminology is going to be, so you should pay attention here. And I'm going to articulate three basic operations, and these operations will inform all of the set theoretic manipulations we will need. From these, we can build other more complex operations.